Welcome to today's NUG community call. I am Charles Lively, and I am a science engagement engineer and HPC consultant here at NERSC. And I am joined by the incomparable Dr. Lippy Gupta, and we are both science engagement engineers. So thank you for joining us for part two in our series. We'll just kick things off with a little bit of just a few housekeeping things, then a little review as well of what we learned in part one related to understanding CUDA device constructs and device host and device hardware constructs as well. Today, we're going to try to get through as much as we can related to learning about kernel-based parallel programming and multidimensional kernel configurations, as well as CUDA memories and tau parallel algorithms. We'll try to get as much through as we can, but we want to make sure we leave enough time for everyone to toy around with the hands-on activities that we do have. Lippy, Helen, any thoughts or words that you have to add? Or Annette?
No, just thanks everyone for being here, and hope you enjoy the last part of this series.
Yeah, I'm good. Enjoy learning.
Okay, awesome, awesome. Well, thank you all for joining us again. We're a part of the user engagement group. This is our team if you don't know us. If you have any issues or problems, we're the frontline people that you can reach out to. So always available either through a ticket, Slack, or even email, or setting up a Zoom meeting too. And so if you have not joined the NERSC user Slack, we encourage you to make sure that you become a member of it. So that way you can network and talk with other users that are doing similar science that you might be working on and working on similar applications and problems. I think having a community is important because research doesn't happen in a bubble. And, collaboration always fosters innovation. So we encourage all of our users to participate, interact with one another, engage with other users as well as NERSC staff, and let us know how we can best help you. Okay. So all of our training events are recorded. If you missed part one, you can go to our YouTube channel and part one is posted, or if you need to re-review after this, and once the part two is posted, we send out an email when that video recording is available as well. Any information about upcoming and past events you can find on our website as well. And these slides are also posted in the Q&A doc as well for everyone to access. Okay, so please, make sure that you, utilize your first and last name. We have our Google Doc as well as our survey are included as well. So if you do not have the GitHub repo clone, we encourage you to go ahead and clone that. And as a matter of fact, let's take about 5 minutes now to allow for people to do that. And that way we can get started with our quick little review of what we learned last in part one. So let's take let's say about 5 minutes to allow for everyone to get started with that. And then we'll go through some examples. So you can clone the repo. First log into Perlmutter. So let me go along with you and share. And you'll just want to make sure that you have cloned the repo. You can do make to compile all of our examples. And so let's give everyone a couple of minutes to get situated, and we will get started first with our initial review of a few examples from what we learned last time before diving into new concepts. About 5 minutes. And if you could, once you have the GitHub repo set up and you're ready to go, just give us a thumbs up so that way we'll know when we can move on. But we'll move on in about 3 minutes. But if you can confirm with a thumbs up, that'll be helpful. So another important thing to note is for today, we do have a reservation and it is CUDA underscore C underscore part 2. So within the repo, you'll need to just make sure you make that change to the reservation that is being used as well. And we have this reservation for you to toy around with and play around with in the training accounts until tomorrow. So feel free to, make use of it and try out some of the examples that we have. Can I get a thumbs up if you are good to go and you've been able to clone the repo and everything? Okay. All right. So if you recall in our part 1, we learned a lot about working with device code and device kernels and host codes as well. And so, we just want to recall a few of the constructs that we utilize where we're launching a thread and using CUDA device synchronize. So who can tell me what CUDA device synchronize exactly does? Any volunteers? So it's basically, you want to recall that it's basically a blocking mechanism, and that's just telling CUDA to synchronize and wait for all threads to return, right? So if we were able to compile and execute this, we're just going to get a couple of hello world statements that are going to also show the ID of the thread that it comes from as well. Okay. So if you want to submit this, you can either do a interactive submission or you can just do the SBatch and submit the file. So you can do sbatch and then hello.sh. It should just take a few minutes for that to run for us. I already have one output. And so again, it just shows us again, hello world. It's not I guess it's not a programming training or course if there's no hello world reference, right? And so this is basically showing us each of the threads that were executed and returning for 10 for each thread. And so we can also try the same thing with our other example. And so if we want to take a simple example like what we learned with the dot product example. And so again, within this, it's a little bit more detailed in constructs in which we have different threads and blocks that are being utilized. We're going to go into a lot more detail about these constructs later. So just look at a little bit of the code, make note of some of the assertions for synchronization as well as how we are able to allocate the memory appropriately for on the device using CUDA malloc, if you remember. CUDA malloc is what we use to allocate that memory on that device. And in this case, we've allocated memory for 3 data arrays here. And then we'll have CUDA memcopy, in which we are able to copy those vectors from the host to the device as well. So let's take a few moments to allow everyone to look over this example, some of the coding constructs, and we can move on from there. So let's take about 2 minutes to make sure everyone is able to go through and access it and see if anyone has any questions or need any kind of clarification on any of the constructs that we have here. Alfred, you want to make sure that you update the reservation. So in the reservation line, you want to have it CUDA underscore C underscore part 2. Yes, you should run make first. So all you need to do is just run a simple make command, and it'll compile any changes that have been made. But if you attended part one, it might not need to make any, no changes might have been made on that part. Alfred, are you good to go?
Do you mean, let me see, do you mean new underscore CUDA underscore C2?
Yes, just like this. So you can copy what Helen pasted earlier. Just copy that whole line here.
Okay, I saw it. Thanks.
Okay, awesome. Anyone else? Patrick, sorry if I'm mispronouncing your name. Are you good to go? Were you able to run make and get everything compiled?
Oh yeah, no problems. Thank you.
Okay, just making sure. Okay, and so that was just a brief, review of some of the concepts that we learned about last in part one. So now let's get back to what we are going to be focusing on for today. Okay. And so if you're not familiar with any of our running jobs or interactive jobs, our documentation is very detailed and showing you how to make use of that. So we encourage all of you to do that as well. All right. Okay, and so what we're going to do now is we're going to get started with basically understanding some constructs required in order for us to create CUDA kernels. And so essentially what we're going to learn about is the declaration, the built-in variables, and also one of the important topics is related to thread indexing as well. Okay, so let's consider that we have this simple example right here. Okay, so within this, what we see is that we're able to declare our device code here. And we are going to declare a vector add kernel that we can utilize. And within this vector add kernel, what we see are a few different things that are occurring. So at the first and foremost, what we see here is that we are able to see that each thread is going to be handling different aspects. And so we have our thread index.x, block dimension.x, and our block ID.x as well that we're coming together, and that creates the global scope that we're going to be making use of. So what we want to do is on our host side, we want to launch enough of the blocks so that we're going to be able to cover all of the elements while we're computing a ceiling. And what this means is that we're going to use a DEM3 structure for that. Always forget about my animations. So what we do here is we want to apply a ceiling, and this ceiling is basically going to make sure that that there are enough threads to cover all of the elements that we have. So we have to minimize my the little participant window. Okay. And so with our vector add, what we're passing in, this is what's going to actually be launching on the host code for that. And so then with additional, what we have here is also declaring the dimensions that we can utilize. And then we're passing that in using our additional constructs here for the dimensions of the grid, as well as the dimensions of the block, and then passing in our arrays as well. Any questions? Okay. So now what we want to kind of focus on is trying to understand the kernel execution. And so this diagram provides us with a good understanding because on the left, we have our host code that is going to be able to launch as the host code that's going to launch that kernel. And then on the right, we have the GPU is going to be able to execute it across many of the different blocks that are occurring. So essentially what is going to happen is we have each thread and it's going to be scheduled onto our streaming multiprocessor. And within the block, we have those threads that are going to come together to basically collaborate and combine their chunks of data together. And again, it's just going to repeat that process for for elements based off of the dimensions being passed in. So here we have 1,000 elements and 256 threads. And so, how many blocks do we need? Anyone want to take a guess? And so it would be basically about 4 blocks. Does anyone have an understanding of, or would anyone be able to tell me why exactly it would be 4 blocks?
Is the ceiling of 1000 by 256?
Right. So with that, the ceiling is going to push it to 4 or 3.9 to 4. And so that's just going to round that up. So it's just a simple, that kind of calculation. Any questions on that breakdown? Okay, so now what we're going to do is focus a little bit more on some declarative elements that we can focus on. Yeah, I always forget about my animations. Okay, so let us consider what we have here. We have a couple of different keywords that we can utilize whenever we're using CUDA. And so we have our device float, and that's basically saying that this is going to run on the device and it's going to be callable from other functions. So it can be callable from the host or from another. With our device declaration, it's executed on that device, and then it's only callable from the device itself. With our host declaration, that's optional, but it executed on the host and it's callable from the host as well. So these are some of the constructs that we can use. And it's another thing, you can use device and host can be used together as well. So those are the basic function declarative constructs that we would use. Okay, so now let's consider what actually happens under the hood when we're compiling a CUDA program. Okay, so essentially, CUDA integrates with C programs and provides for that CUDA extension. So we use the NVCC compiler from NVIDIA, and that is able to compile both host code as well as device code for us to use. And so the host code is going to be sent into your regular C, is sent as regular C, C++. Then the device code is compiled into our intermediate assembly, and then we get to execute that runtime with the GPU and NVIDIA. It uses a just-in-time compiler for the hardware. So that allows for us to, make mixed use of combining and utilizing both CPUs and GPUs and other computing units that we could make use of as well. So this all leads into the ecosystem of heterogeneous computing that is prevalent now for most of us. Okay, so we've just gone over a little bit of some declarative components. So now we're going to try and take that and apply it to multidimensional grid. So, we're just moving from, 1D and 2D constructs to more three-dimensional constructs because we live in a 3D world. So that is more accurate for us to make use of, right? And so here, what we just want to try and focus on is making sure we understand how multidimensional thread indexes work and how to map them to various data coordinates and whatnot. Okay. So what we have here is we have an example of our multidimensional grid. And so we can see that the grid is made of blocks, and the blocks are made of different threads as well. So this is kind of giving us an illustration of from 2D into 3D. So here, this is where we have scaled it up from the block dimensional size. And so we have a 3D configuration for each one of those. So you can kind of think about it as like like a big poster that's being put into small little squares and chunks. And that's where we're assigning our threads. Each thread will do a chunk of the work for us. And so with this example, what we have is, again, we can partition our dimension into different blocks, and the blocks are what we can make use of. So here we have our 62 by 76 pixels example, and then we can divide it into 16 by 16 blocks for divvying up that work. Okay, so one thing that we also want to understand is, just a row major layout that we can utilize. This is, just a refresher on how we store arrays. And, in C, we store them row major order. So, rows are consecutive in memory. And so, we basically are going to get the formula row times width times the column. And that is what we do to coordinate or convert from the 2D to 3D. And so with here, this would be where our calculation would occur. And so we're going to use a really kind of simple example to kind of illustrate our points here. And so let's consider that we are making use of what we would call a CUDA kernel that's going to be doing an operation on a picture. So who can tell me with this, how many dimensions are we working with here?
I'm sorry, you mean the dimension on the device or the overall dimension?
For this representation.
Oh, it's just on the device you have a block dim and also which is a size and also the thread. So multiply together, get the total row index and co-index, column index.
Right. So in this, we have an illustration of how we have it as a 2D illustration of it for, an M by N, or matrix. So let's, and was that Beijing? Beijing?
Yes, sounds like let's begin in the beginning.
Okay, thank you. Thank you for those points. And so in this example here, what we want to see is we'll have the host code for launching the kernel that is going to execute. And so with this, we'll use various dimensions that are being computed, and we say n by 1 over 16 plus 1 by m by 1, m minus 1 over 16 plus 1 as well. And then we're passing that in as 16 by 16 blocks. And that's illustrated here with our again block declaration. Okay. So let's also consider moving on. So in some cases, not all threads will be able to follow the same kind of path in which we do the computation. So that's kind of like what we call a little bit of divergence. And so essentially what that means is not all threads in a block are going to be able to follow the same control path. So when that happens, we have to have a little bit of coordination that is going to occur. And that can, in some cases, cause some threads to branch and others may branch in another way. And so with the divergence, the GPU is able to handle that by executing each branch serially. So we don't have a kind of like a performance degradation. So this is kind of what we're focusing on in understanding that example. Okay, so now we're going to continue to expand our knowledge a little bit more. And so what we're going to do is focus on understanding how we can extend multi-dimensional kernels into real-world examples. And we're going to do like a couple of picture kernel examples that can be used to illustrate our points. Sorry, I hope there's a moving truck, and I hope I don't hear too much noise. Is there any, do you guys hear any background noise or anything?
No, actually,
Okay, good,
pretty
perfect.
good.
Yeah, Zoom noise cancellation for the win. All right. So what we want to consider is in our RGB color image representation. So what we have here is we just have, each pixel is an image and it is a, RGB value. And so each row is just, based on color scale as well. So you can have, the ranges are not distributed uniformly though. And that's what kind of, gives us the different colors that we have to work with. So if we have a vertical axis, it's going to be our Y value, or horizontal axis is our X value. And it can show exactly the fraction of the pixel intensity that you have to work with. So, and then that remaining fraction, is just going to be computed as well. And so it kind of gives us the triangle that is representing the representable colors in this color space that we're going to work with. So, on the right, we see the Adobe RGB color space being visualized for us with the different combinations that we can work with. So essentially, what would that mean? Conceptually, and we can take it to a real example. And in this case, it's going from, a RGB color base to a more grayscale base. And so we see here that the grayscale digital image, the pixels of each value vary based off of only the information based off of the intensity of it. And so really what that means is kind of like a grayscale kind of keeps the brightness and then kind of discards some of the hues and other components that would be represented. So you could kind of think of it in that way. Okay, so how exactly will we need to compute that? And so we could do that really easily for each pixel by using a dot product. And so we have our, gray pixel that we can make use of, and we do the dot product based off of the pixels RGB vector and then other fixed constants. And then, so what we see here is what's being passed in, and you notice that each of the RGB values are different. So that is the intensity that we are illustrating to focus on. So for here, we have the intensity of being about 21% and green 71, and then the blue is 7. And so that is what basically is going to cause the transition to the grayscale for us. Does anyone have any thoughts on what might happen if we were to swap any of the values?
They probably have a different way of mapping the color to grayscale.
Right. And so what intrinsically, what might that look like?
The gray color kind of changes for the output picture, or no longer a good way to represent the colors.
So so let's say we were to swap red and green. Basically what that means is that if we gave red the highest weight, then it would kind of appear unnaturally bright because the redder tones would dominate. And then like the darker tones from the green or blue would be like foliage. But like, let's say, what if we, I don't know, gave blue a significantly higher weight? If blue were given a higher weight, then what that we would just have a lot of the other tones, like the sky, would blow out, but other details would fade. So coordinating and figuring that out is just a waiting game to see which one you want to focus on. And, you know, that's just an illustrative example for us to work with. Okay. And so here we have our example in which we can just simply do the grayscale conversion of the code. And so within CUDA, we have the picture kernel that can operate for us to implement that grayscale. So with each thread, what we have here is we're going to compute each of the threads and the grayscale value for one of those pixels, right? And then we want to also compute the coordinates for X and Y so that and flatten it to a 1D index for our gray offset. And then once we have that, what we're going to do is use this to compute the corresponding RGB offset. And so that's going to be the gray offset times 3 value. And then what we'll do is we can load those values appropriately, compute the weight sum, and then store that grayscale image as well. And so one thing that you want to make sure to understand is always verifying you know, your boundary conditions and the chunks that you're going to make use of. And with that, remember, X is going to need to be less than the width, and Y is going to need to be less than the height. And who can tell me what happens if you were to not follow those conditions where X is less than the width or Y is less than the height? Anyone want to take a stab at it?
The gray offset will be wrong because it goes out of the picture in some sense. The interpretation of the new index for the RGB will be wrong, I think.
Well, at another level, well, if we were able to even get to that point, because what would happen is we would have, you know, out of bounds memory access. So, you know, that's why we have those conditions.
Yeah, thank you.
Good. Thank you for participating though. Okay. Okay, did we have any questions thus far?
Yeah, I just have a question. Do we, for a code like this, do we always need to calculate how many threads are enough for a specific picture? Because the picture, or do we may need to write a kind of a function to every time calculate how many threads we need, or is there an automatic way or a function we can call directly to solve such similar problem?
Okay, that's a good question. So depending on the scenario that you want to do, in principle, you know, with this example, we have our weighted dot product that we're going to make use of. It doesn't always need to utilize CUDA kernels. Sometimes it can be on the CPU. But if we want to utilize the CUDA kernels, we'd have to compute those chunks appropriately.
Okay, thank you.
And so that would be like, the thread is going to be the smallest worker, and then we have the different chunks. So the more data you have, the larger the chunk can be based off of memory. But typically it is, it's a coordination game to determine what might be that optimal block size. And it can vary based off of the memory that is available on that GPU that you want to make use of. So with the grids, we have these, kind of collections of chunks that we can make use of. And so that's what the index is going to provide us with that position inside of the blocks. And the block ID will provide us with the position inside the grid. And the block dim will provide us with the number of threads in the block that we want to use. So in some cases, we can do like some scalability testing to kind of determine what might be the optimal block size that we want to utilize. Does that make a little bit more sense?
Yes, thank you very much. That's very helpful. Thank you.
Okay, and so, yeah, basically with this, that's how we do those, coordinate that. Good question, though. Did we have any other questions?
I have a probably trivial question. When we access the RGB values, there's a +2 and a +3 to the offset. Should that be 1 or 2, or am I missing something here?
You kind of cut out, I heard +2 and +3, so I thought you were talking about maybe these for the green and
Yes,
blue.
yeah, exactly these values. Why +2 and +3? Should that be, I would have naively thought +1 and +2.
Okay, so all that is just indexing into consecutive chunks.
Right.
No, what he's saying is that the offsets are incorrect. They should be 1 and 2 because it should be offset
Oh,
+0 offset
that's
plus
right.
1 offset +2.
Even so on this one, it's corrected. So good catch.
Okay, good. Thanks. I just wanted to make sure I'm
Good
not missing
catch.
something there.
I'm sorry, I misunderstood. Good question, though. Any
Thanks.
other questions related to that? Because the +1 and the +2 is going to be the green and blue channels that we'll use. And so basically each of those pixels, they sit next to each other in memory. And so when we step through, for adding, 1 for G and 2 for B, we see that as the +2 and the +3. And so here we have, really it's 0, 1, 2 is what we have. Okay. So now let's continue on to a little bit more advanced concepts associated with how we're going to learn about a 2D kernel and how it is used to do complex computations and memory access patterns. But first, I want to take a moment. I want everyone to just take a few moments and go to our repo. And if you have not, I want you to work on, make sure that you can execute and run at least the hello world example, as well as the vector add example here. And let's give everyone about 5 minutes to execute those for hands-on experience for a little bit. And then we will continue on into our next part of the training. Just give everyone about 2 or 3 more minutes. Okay, if I could just get a few thumbs up if you were able to execute the kernels appropriately. And again, the batch submission scripts are already there. Just make sure that you change the reservation to CUDA. It's CUDA_C_ part 2, and you'll have that reservation available for you to make use of until tomorrow evening. Okay, so we'll continue on now. So we focus a lot on our focus is going to be on how we can do the 2D kernel can be more complex. And so now what we're going to focus on is understanding how simple kernels for image scaling and color conversion can, be utilized. And so this is going to allow for us to build a 2D kernel that can do complex computations and also has complex memory access patterns as well. And that's kind of how, behind the scenes image blurring really does work conceptually. And so here we have just an example, and the big idea that we want to kind of take away here is that, we have we're mapping one pixel directly to one type of output. And then what that means is each thread is going to compute the average of pixels in that surrounding box. And that basically becomes the blur window that you make use of. So we can see here that we have each thread block is going to possess a chunk. And those pixels are going to be processed by that thread block. And so for each pixel, we average over it with the 2D blur region. So a question is, if each pixel depends on its neighbors, what happens at the edges of the image? Anyone want to take a stab at it? Well, essentially, what that means is that we would need to have boundary checks. So the kernel does not, is not reading from invalid memory. So that's another kind of consideration when you don't have when you have edges that do not have neighbors. Okay. And so how exactly would we implement the image blur as a 2D kernel? And so in this case here, what we have is we do have the blur kernel method that we have created. And with it, we have each thread. It's going to appropriately identify the rows and columns in that image that need to make use of it. So what happens is it will identify that, and then it's going to loop over over the 2D box around the pixel, and then it's going to just accumulate that value, and then it computes the average of it. And so what that means is that we have written out our blurred kernel method. And so flushing that out, we have our pixel values that we utilize that we want to sum as well. We get the average of the surrounding based off of that blur size for the box. And then we have appropriate constraints as well. Okay. Any questions on this code snippet that we have here, where we have our blower and blur row and blur column constraints that are being used? So we have the blur size we have set here is going to be 1. So that's just meaning we have a 3x3 window around that pixel. And then we can use cur row and cur column to basically coordinate with each of the neighboring pixels that are being used. And so with each neighbor pixel, the boundary checks are going to be used to prevent it from going outside of the image, which is what happens when we say around the edges. And then we can have that blurred value that is computed and average, and then it gets written to the output array. Any questions about that? Okay. So next up, what we're going to do is focus on understanding the hardware execution and essentially how a CUDA kernel utilizes that hardware to secure resources, how threads are assigned to blocks to execute on the sources, and then also a little bit about on capacity constraints for executing those resources and zero overhead thread scheduling as well for it. Okay. And so what this means is that we just want to have a good understanding of how we can make our kernels scalable and, apply, scalable and efficient for use as well. So one thing that we want to consider is one of CUDA's biggest selling points or strongest strengths, I would say, is that it focuses on transparent scaling. So what that means is like each block is independent on the GPU. So you can run them in any order on any of the streaming multiprocessors that we have access to. So if you run it on the more SMs you have, then the more blocks that you can run in parallel. So if you have fewer SMs, and that's fewer blocks, and then the queue is longer for you to utilize. And so what that means is that, for the same kernel code, we can scale it from a small scale GPU up to an even larger GPU as well. So if we were to double the number of streaming multiprocessors, what would happen to our performance here? Or in theory, let's say we were to double the number of SMs that we have available to make use of. How might that affect our runtime or performance? Positively or negatively? Well, you have more blocks, and that means there's more resources for you to make use. So if it is a scalable algorithm, it should result in a performance improvement or a decrease in execution time as you add more threads or more blocks. Just like a little, the more resources you have in coordinating and splitting up the work, the more that you can get done. Okay, so let's kind of take a simple example where we can illustrate how SMs are able to handle blocks. And so what we have here is we can have the threads that are being executed on on each of our resources. So what we can do is we can utilize up to 32 of those blocks to make use of them appropriately. And then let's minimize that. And so what that means is that for each of the SMs that we can run multiple blocks, and as long as there is enough resources for us to make use of for that block, so we have to have enough threads that we can utilize and registers available for us. So this block size basically means that we can have 8 blocks by 256 threads each, or 4 blocks by 512 threads each as well. So, but CUDA's runtime scheduler decides essentially how to fit the blocks into each of the streaming multiprocessors. So a simple question, or maybe not so simple, if each of our SMs, we can support 2048 threads, how many 256 thread blocks can we fit in at once?
Eight.
Right. It's going to be about 8 blocks. Okay. Any questions or on those topics or concepts?
Yeah, my question is, how does the number of blocks matters here? Or just they can just see 2K threads, that's all, or blocks matters in some sense?
Okay, that's a good question. So each block of the thread is what we're going to be scheduled as a unit. So with the SM, we can hold multiple blocks at once as long as we have enough resources. So on like a Volta NVIDIA GPU, they can go up to 248 resident threads. So the number of blocks and the number of threads in each of those blocks will directly affect that capacity. So let's say if we have in our example, or the question you previously answered about the 8 blocks, that's going to fit perfectly and allow for full utilization. But if you only launch 2 blocks across the whole grid, then only those 2 blocks will ever run and you'll just be using a fraction of it. And so you can also incorporate a little bit of latency hiding into that, where each block can contain a warp, and then that warp is a group of, 16 or 32 threads, and that can be utilized to also schedule the warp to hide memory latency.
Yeah, my question is more like if I only have one block with 2,000 threads, how is that different from 8 blocks with 256 threads each? I'm still.
Yeah. Performance-wise, that's the capacity of the resources, so that's similar.
Okay, so why do I need to break that into 8 blocks if I'm also using the full threads, all the threads with just 1 block?
Repeat that one more time. I'm sorry.
Oh yeah, sorry. It just I'm considering for the case 1, I'm using all 2048 threads just with 1 block. And case 2, I'm using 8 blocks with each having 256 threads. What's the difference between these two in terms of? I think I'm using all the resources, all the threads, but one is have a huge block, and one is I break that into 8 smaller blocks. So what's the difference for actual computing?
Oh, okay. I think so. I completely was kind of understanding what your question. So, it's basically giving you the capacity of it. So it can be up to 248 threads. So let's say you wanted to use case 1 is just an example. It's providing you with all slots being filled perfectly. Case 2 is 512 threads per block, and that's going to need additional of 4. It's going to be 16 of the warps per block, and then we'll need 4 blocks, and that'll fit onto it as well. So it's both are offering full processing, but you can use fewer larger blocks, and each block can do more work. But fewer blocks are also not are available for, the load balancing in that aspect. So it's just basically kind of showing you different configurations that you can use. Like if you need to make use of many small blocks, then you can use that for scheduling flexibility. So
Oh,
it's just
okay.
block size.
Okay, thank you. I think
I'm a
it's
little long-winded on that response, but it's just, you know, it takes a little bit of nuance to try to explain it that way.
okay. Thank you very much. Yeah.
Does that kind of clear up? It's kind of about the granularity of the resource utilization is what it affects. So with that 256 thread block, you know, you're going to have more blocks in flight. So that's like 8 versus 4. And that's just more granular.
Okay.
That
Yes.
allows for more flexibility with scheduling. Like for say let's say we're in our queue or our reservation today, we're using um, shared resources. So if you try to fewer blocks will likely get you scheduled quicker, essentially, if that makes sense.
Okay. Yeah. Thank you very much.
Okay, cool. Any other questions? Okay. All right. And so again, we simply want to focus our attention on understanding the memory model that we make use of, and just, you know, our traditional CPU model, von Neumann model, if you are familiar, or, you know, is a CPU model where we have our memory, our ALUs that can registers, our control unit, and all are connected for us to do our instruction processing and streaming and whatnot. And each cycle is going to take a bit of instruction and do an operation on it. So this is a general model, but it's not designed for massive parallelism. So a updated model with the von Neumann, which includes single instruction, multiple data units as well, is that we are able to extend it for GPUs in that a single instruction can broadcast many threads at once. And then each thread can apply its own data element. And again, this is how the GPUs are able to achieve the throughput appropriately. So with our SMID model, that's going to be helpful for image processing because it's good at helping each pixel can then be transformed into the same operation in parallel. So this is kind of like some of the kind of the changes and expansions to the memory model that have been incorporated for GPU processing. So how do we consider warps as scheduling units? A simple example is that we have each block is going to be, you know, executed as 32 thread warps. And so each of those warps is an implementation decision and not necessarily a part of our CUDA programming model. So what happens is the warps are going to scheduling those units in our SM, and then the threads in the warp execute in the SIMD. So as we move forward, future GPUs are going to have a lot more threads and other capabilities and resources that we can make use of. So all the warps would be active, and the scheduler picks which warp is going to run next with that. Okay, so let's also consider, let me check we will make it a couple more slides, and then we'll just allow everyone a little bit more time for any of the hands-on exercises to walk through. So let me reach a good stopping point shortly. Okay. So in this simple example here, what we just are focusing on is understanding how each of those blocks will execute. So we have those 3 blocks that are executing. Each block has, again, 256 threads that it can make use of. And then each of those blocks are divided into 256 by 32, which is going to give us our 8 warps. And so in total, that gives us 24 warps that we are going to be executing on our SM. So with this, we're going to continue on. So let's, a question that I do have that I would like to pose to everyone is, let's say if half of the threads in a warp were taken one if branch and the other half take the other else branch, what would happen? And it kind of relates to what we initially talked about, and that essentially they would both execute in parallel because that's just what we call the branch divergence. So, and it reduces the efficiency. So just a little question for everyone. Let's see, next thing that we want to consider is with our thread scheduling example. So what we want to do is we got to keep track, each SM has to keep track of which of the warps are going to execute with the warp scheduling. So if one warp is waiting on memory, then the SM is going to switch to another warp that's ready instantly. And what this does is it hides the latency and it keeps the GPU busy while we get more data processing as well. And so this is better than how CPUs hide latency. And a lot of it is because CPUs are going to use a lot of deep caches and, you know, other branch prediction mechanisms if you refer back to the von Neumann model. But with GPUs, it just rely on the multiplicity of the warps available. And that's a way around hiding or masking any possible latency. All right, so other considerations that we have to take into account when we're trying to chunk up is this is going to be related to understanding how we can best consider the block size that we want to use. And so, you know, Beijing, I think you asked earlier about determining the size, and really it's just it can depend on the resources you have available and how much data you are looking to work with. And it's important to note because choosing that block size is going to affect the utilization. And if you're on a node and you're sharing it with other users, that's going to kind of prioritize the resources you have access to. So, you know, on some NVIDIA GPUs like the Volta one, the SM can support, you know, 2048 threads and up to 32 of those resonant block. So if each block has 16 threads, we could host 128 blocks, but the 32 block per SM limit kicks in, so only 512 of those threads are used. And so that could result in us wasting our resources, right? So let's say if we have each block has, you know, 64 threads, then what that means is we have 32 threads, 32 blocks that are going to fit perfectly, and our 248 threads are going to provide for full utilization. Now, the other case is if we have the example in which we have 900 threads per blocks, that means that only 2 blocks are going to fit. And so that's going to result in underutilization. So this is just kind of like how you have to determine the optimal block size because you want to essentially achieve full, you know, utilization for efficiency. Okay. And then we will just finish up with understanding. Okay. So I think we are at a good place to stop and allow for people to do some work on some of the hands-on exercises. And we did not get as far as I initially planned, so we might end up having a part 3 if everyone would be interested in that. I'll send out a poll to all attendees that we could, if you would be interested in a part 3 where we can discuss in more detailed CUDA memory constraints and efficiency and optimization for it with some of those examples. but let's take a few moments and allow for everyone to just have a little bit of time to maybe work through any of those examples. And did we have any questions in the Q&A or in the chat? I'm sorry, I wasn't. Oh, you're welcome. Were there any other questions? And if you could, if everyone could take a moment and fill out the survey for us. NERSC is a user facility, so we try to have these different community calls to be of interest to all of you. But if you the more feedback and thoughts that you give us on topics that you want us to have more community calls on, we would welcome that. As a user facility, it's our goal to make sure our users are using our resources efficiently. And this whole series actually started out as several of our users wanting to learn a little bit more and understand how to incorporate CUDA into their applications and simulations, or just learn a little bit about it. So we're a part of NVIDIA's teaching academy. So we have resources and materials that they provide to us for us to facilitate these type of trainings for you. Okay, the survey, let me go ahead and update that. I can do that really quickly. So we can change the access for everyone. So I have updated it now, so you should be able to complete it. If you wouldn't mind checking back again for me. Is that good, Alfred?
Yes, it works now.
Okay, thank you. Do we have any other questions? Could I get a reaction if you would be interested in us doing a part 3 where we continue on with more advanced understanding for the memory model for GPUs? Okay. All right. Well, I think we might have a winner then. So we'll probably launch this as a part 3 for next month, where we can go into more detail with also some more examples as well to work through. Did we have any lingering questions or thoughts? If you could, please go ahead and fill out the survey for us. Your feedback matters. So. All right. Well, with that, I think we can call it a day for today's community call. Again, thank you all for attending. Again, all resources and materials will be posted on the event webpage, as well as the recording of this event as well. And an email about when the recording is available will be in our weekly email next week. But thank you all for attending. I hope that you have a wonderful week and happy programming. Thank you.
Good job, Charles.
Thank you. My throat. I was like, oh, this is long.
I know. Yeah, you got to keep some tea with you.
I know. Yeah, I have some. Actually, I do.
But then you have to drink it.
Oh.
I know. Good. Okay, good job. Very well done. Yeah, basically no real questions in the Q&A, so.
I
Just
think
one, and I just answered it.
Oh, nice. Okay, good.
Mhm.
All right.
Yeah. Good good pace.
Yeah.
No, I thought so too. I
And
was like, I
people
was
have
a little
time to
worried.
do hands-on. Mhm.
Yeah.
No, I think people were really participating, which was